to get us started on this lesson, it says modeling with exponential and logarithmic functions. We did do other modeling back in the fall. We modeled with linear and quadratic functions. So the process is going to be the same. Those of you guys who remember the little foldable, we did have this same foldable last semester when we were doing linear and quadratic modeling. So the only thing that is going to change with the lesson today is which type of regression you choose. So when we get to the calculate menu in the calculator, you're going to have to determine which type of regression to use. That is the challenge today. Other than that, everything is going to be in the calculator. Sound okay? Okay. So to get us started, I have given you 6 different graphs down below, and then 6 types of functions here. So I'm going to give you about 30 seconds. That's all we're going to take. I need you guys to, based on the shapes of the graphs, and some of them are a little more challenging than others, I need you guys to determine which function goes with which graph. This one. Linear positive. How'd you figure? How do you know this is linear though?
It's a straight line going up.
It's an exact straight line. Now how do you know it's positive? Because it's going up as we move from left to right. Okay, good. So this one is linear positive. Cool. All right, keep matching. The rest of you guys, keep going. Keep going. What else can we get? Okay, so a little bit of process of elimination. Can anybody give me B?
Linear.
What's that one? That's linear negative. Okay, so that one's pretty simple. Linear negative. Okay, so this one I thought was just a little bit tricky as far as the quadratic was concerned. They actually did a quadratic for F, but they shifted it. So usually a quadratic goes through 0, 0 here, but this one they actually shifted it down. Okay, so I wish they had left it with the parent function or close to the parent function, but they didn't on this one. So this one is actually a quadratic here. Okay, so we got linear, we got quadratic, linear positive and negative. Okay, what do you guys think this one is? Why is that one logarithmic? You're right. No clue. Sounded like a good guess?
Oh, because it's going upwards, but then it curves towards a point on the graph.
What do you mean curves towards the point on the graph?
So like whenever we were taking a number, so like you put it into the calculator and it wouldn't hit that number, and it's doing that for 6.
Okay. So logarithmic functions were the ones that kind of went out like this, and they do kind of start to have an asymptote. They do kind of start flattening off. So this was, if I was to extend this out, does it look like it would kind of start flattening out that way? So that one is going to be your log function. This one is log. So we have exponential and cubic to have to be concerned with as well. So let's see. What do you think this one is?
Cubic.
That one's actually the cubic one. And then this guy down here, by process of elimination, this one is your exponential. Let's take a look real quick. The shapes of the exponential versus the quadratic. Very similar in those 2 shapes, right? Okay, so sometimes we may need something a little more than just the graph to help us figure out what type of function it is. And that's going to lead us into what we'll get into on the next page. The data can actually help me figure out if it's exponential or quadratic as well. Okay? So then the next part of what we want to do for all 6 of these is actually come up with an equation that would represent the data. So if you'll notice, all of these are points. We call those scatter plots. You all are familiar with scatter plots, right? I did some of those in Algebra 1. I don't know how much you did in geometry. But a scatter plot is basically just a plot of points, right? So what I need you guys to do is on number 1, we'll just start with this first one and make it easy. I need you guys to give me some coordinate points. So pull me some coordinate points from this table or from that graph. What do we got? And I only need 4 of them. You could use all of them, but I think 4 is good enough for us. So give me some coordinate points. What do we have for this table or for this graph?
What the points actually are?
Uh-huh.
Okay, then 2, 2.5.
2, 2.5, that one right there?
Yeah.
2, 2.5. Okay? Somebody else, give me another coordinate point.
6.5.
6, 6.5. That one sounds good. 6, 6.5. Okay, give me another coordinate point. What else we got? 5, 5.5. I'm thinking maybe y'all are coming up with a pattern. You think? Yeah? Okay. What's another one? 3, 3.5. That works. Again, I just had room for 4 points on the table. You could actually go through and do all, how many are there? 1, 2, 3, 4, 5, 6, 7. So we could use all 7. I just only have room on the table for 4. Okay? All right. We are going to have the calculator determine an equation that would go through those points. All right, guys, we are back up and running. So I'm going to just kind of start from the beginning, even though you guys have already done that part, to kind of have it in the video because I'm just going to try again. Okay? So what we're working on today is modeling with exponential and logarithmic functions. You guys have done this same kind of modeling with linear and quadratic functions. This is all going to be calculator based. So what you're going to have to determine is which type of regression you're going to need to be doing. Other than that, you're doing everything in the calculator on these. Okay? So the first thing I'm having you guys do is determine which graph goes with which function. And we're doing that based off of the shapes of the graphs. So somebody give me one that you're pretty confident in as far as which function goes with which graph. What do y'all think? Good. A is linear positive slope. We know that because we are going up by exactly the same amount each time. And we know it's positive because we're going up, right? So this one is going to be linear with a positive slope. Okay, so we did that one. All right, give me another one. Good. D is linear with a negative slope. So same thing. We're going down by the same amount each time. So this would be linear negative. Okay, that's this guy. All right. So just in general, what does a quadratic look like? So not worried about the functions down below, but in general, what does a quadratic function give you when you graph it? If you don't know these at this point, we probably need to start studying those shapes because at the end of, like before we do final exams, that's going to be one of the things that I'm going to quiz you guys on, is all the different shapes that we've covered this year. Okay, a quadratic goes like this. What do we call that? Starts with a P, parabola. Okay, so a quadratic is going to give you that parabola top shape. What about a cubic function? That was one of the polynomials we covered. Cubic functions look like this. Okay, they may or may not have that little extra hill in the center. All right, these two we just did. What does an exponential function look like? Has an asymptote coming across this end, the bottom like this, horizontal asymptote, and then it follows up along like that. That's exponential. All right, so then logarithmic, because those are inverses, logarithmic has a vertical asymptote. It follows the vertical asymptote and then flattens out across the top. Okay, so now that I've given you those, does that maybe help on a couple more matches? Or at least one more, right? What does B have to be? B is logarithmic. It's the only one that kind of curves down like this versus the other ones down here curve up. So this one is your logarithmic function. All right, these other three are a little bit harder to determine between the three, and it wouldn't be a situation where I would give you those three and say, hey, pick between those three necessarily. So this is just kind of an exercise that we got started with today. So this guy here, because it is going through the origin 0, 0, it could not be exponential. Exponential functions, unless they are shifted, don't go through 0, 0. So this one actually is a cubic function. And then all we have left between these two down here would be our exponential and our logarithmic. One of them is going to be a little bit, usually is a little bit flatter than the other. So I'm thinking this one should be our exponential. And this guy over here should be our quadratic. And this quadratic has been shifted up. This exponential has been shifted down. So again, basically what I'm trying to get you guys to see is when there is a certain shape on the graph, that's going to tell us the type of function that we're looking for. Okay? So then what we're going to do, and I'm not going to do this for all of them because I don't have the time to do it for all of them, but we are going to go through the process of figuring out these equations in the calculator. And then you guys picked up a foldable today. Those are calculator screenshots. So we're going to write on those kind of where we go to get these different steps in the calculator. Okay, so on A, the first thing I need for you guys to do if we're going to put this into the calculator is we need a table of values. We need a data table. So I need you guys to pull some points from the graph and put them into the table. All right, so pick some points for me. What do we got? Find me a coordinate point or two. Okay, so 2.5 would be fine. 2 and 2.5. All right, give me another one. 4 and 4.5. Okay, give me another one. 5 and 5.5. Are we seeing a pattern here? Maybe. So then what would be another one? Could we do 6 and 6.5? All right. So again, all we're doing is just picking some points from here. You could use all of them if you wanted to in the calculator, but I didn't have enough room to make a table for all of them. Okay, so now we're going to head to the calculator and we're going to type all this stuff into the calculator. This is where I crashed last block, so we're going to see if it works. Not happening, is it? All right, so I need you guys to follow along with me on the calculator steps or on the buttons that we use. So I've got it. You guys follow along with me here on the calculator, okay? So the first thing that we're going to do in the calculator is we need to go to Stat to be able to enter the data in. Okay, so press Stat for me, and you get to this screen right here. We're going to Edit. If you already have numbers in your list, the way you clear the numbers out, so we go up to the list name, so to the very top of the list. And guys, here you press Clear. Do not press Delete. Delete takes the entire list away. Then we have to reset the whole thing to make it actually work right. Okay, so if you're here, you're going to press Clear and then press Enter. That will clean your list out. Okay, I'm going to do the same thing over here with this one. Put the cursor on the list name, press Clear, press Enter. Okay, so once you've been using this for a little bit and you have a lot of numbers in there, you probably want to clear them out so that you can put a new list in. All right, list 1 is going to be our X values. List 2 is going to be our Y values. Okay, so the table that we just used in our notes, the X values were 2, 4, 5, 6. Does that sound right? Is that what we used? Okay, so type those into the X list for me, or list 1. All right, list 2 will be your Y values. So I believe our Y values for this one were 2.5, 4.5, 5.5, and 6.5. Are we okay entering the data in? Okay, so you have to tell the calculator what data you want it to use, and now you're going to have to tell it what type of equation you want it to give you. So now we're going to go back to Stat. This time we go to the calculate menu. So I need you guys to arrow over one to the calculate menu. And then what we're doing by putting our data in and asking the calculator to make me a model or an equation is called regression. So you're going to be looking at these options down here. Any of the ones that say REG, reg, that's regression. So we have a lin reg, a quad reg, a cubic reg, a quart reg. Lin reg, this is backwards, so that would be an inverse linear. LN, wait a second. We've seen LN. What is that? That's a log. That's natural log. Okay, so that's the one we're going to use when we do logarithmic regression. Then we have EXP. What would that be? That's exponential. Okay. We have power. So when you guys are doing your Delta math assignment, it might ask you, and it will actually specifically say, hey, do a power regression. Okay. We're not doing power regression for this, but I did want to point that out. You do the process the exact same way. Nothing changes except you use this option if it tells you to do a power regression. Okay. Some of you may not even see power regression on your Delta math, and that's totally fine. But if you see power, you use this guy. Okay. The last one down here is logistics. There will not be any logistic curves on your Delta math, so don't worry about that one. So we're focused mostly on power up through our lin reg that we have right here. Okay. Now, the way we choose that is we figure out which type of function we were given. So on your notes, you guys told me A is a linear function. Yes? So we're going to use option number 4. So go ahead and select option number 4. All right, this screen is pretty much going to look exactly the same regardless of which function you're using. Up here, it does tell you lin reg, so this is linear regression. You will leave these first 3 alone. You do not change those at all. If you want to graph the equation, once you have the equation created, you can store it here. So all we do to get to that is alpha, trace, and then press enter. So the calculator is going to put it into the y equals for you instead of you having to type it in on your own. Okay, that's all that is doing. So if we want to graph it, that's where we got to graph it. Then we come down here to calculate, and then just press enter. Okay, and then we're on calculate. Your highlighter is, your cursor is on calculate, press enter. Once we get to this screen, here's your function, y equals ax plus b. It tells you what a is. It tells you what b is. So you're going to put a 1 in place of the a and a 0.5 in place of the b. That's your equation. Okay, so the calculator just created the equation for you. So our linear equation for this guy is going to be y equals, what was our a? Y equals, our a was 1, x plus, what was our b? 0.5. And then you might possibly use that model to help you predict other data in the scenario. And that's what we'll get to when we do our application at the end. Okay, so we're going to do it again with the logarithmic function, so with b. And then we're going to get some other practice with regression in the calculator. I'm just not going to go through all 6 of these. We don't have enough time for that. Okay, so on B, pick me some points, just like we did last time. So pick me some data points. 1, 0. Where are you going? Huh? Oh, are y'all just now leaving? I saw you on the list. Okay, they didn't. I don't know that they gave us specific times. Okay, cool. Bye. Have fun. All right, so taking a look at B, we're looking at points. Y'all tell me 1, 0 is a good one. Okay, we are just estimating here. So give me another point. Estimate. 2. And we know it's not quite 2. Maybe could we call that like 2.1? Yeah, it's not quite 2, right? It's not totally on that line right there. It's just a tiny bit above it. So we're just going to estimate maybe like 2.1. Okay, give me another one. 4 and 4.1. Okay, give me one more. So maybe 6 and 5 point, so that's a tiny bit higher. So maybe could we call that 5.2? Like 6, 5.2. Does that work out? Okay, so again, all we're doing here is estimating because obviously these are not exact values. So I'm wanting us to all get the same equation when we get into the calculator, which is why we're doing the points together. But if you guys were doing this individually, we would all come up with slightly different values, which means we would come up with a slightly different equation. Okay, so there's where the variance is going to happen as far as the information is concerned. So we're going to do a regression for a logarithmic function now. The table that we got from the graph, we are going to go to stat right here and edit again. So we're going to put those values into the list. Okay, so the x values we had on the table were 1, 2, 4, and 6. Go ahead and enter the y values in 0, 2.1, 4.1, and 5.2. Again, on this one, we are having to estimate quite a bit. If you guys were doing this separate from me, you might estimate slightly different, which means your equation is going to also be slightly different. I will make sure that you guys, when you're receiving practice or test questions, that's not going to be the case. Okay, so this is just to kind of get us started on these types of problems. All right, so once we have all of our data into the list, we're going to go back to stat. And this time we need to calculate. So we're looking at our options for a regression. Linear, quadratic, cubic, quartic. This is the reverse linear regression. We definitely don't want that one. But we have ln. ln is actually your natural log, and that is the best way for us to do a logarithmic regression in the calculator. So we're going to do option number 9 when we need a log function. Again, if we want to store the regression equation, we can go to alpha and trace, press enter, and then you're going to come down to calculate, and we're going to get our value for the function. So notice in the value, it gives you the entire function here, a plus b ln of x, and it tells you a is this, b is this. You do need to round both of those to 3 decimal places, so our function this time will be y equals 0.037 plus 2.906, and then you put ln of x back behind it. Now that we've completed a couple of the regressions in the calculator, I want to give you guys the steps written down into your notes. So you should have picked up a foldable that looks like this, and to cut it out, all you're going to do is just zigzag back and forth all the way around, and then you're going to fold it like an accordion. So this top part right here, you're going to fold backwards, and then you fold forward, backward, forward, and it'll just zigzag all the way down. You're going to glue that on the bottom of page 1. But we are going to write in some notes and calculator steps into the foldable so that you have to go along with the screenshots, you know exactly where to go to get to each piece. So this first page actually is just talking about how to set the calculator up if you were needing to graph it. So the instructions here are to graph. Okay, we didn't do a whole lot of graphing in the calculator, or won't do in this lesson a whole lot of graphing in the calculator, but I left it on here in case you want to be able to see it. So we get to this screen by going to y equals. So I put a little box around it like that to indicate that's the button that I push. And when we get to y equals, we have to turn the plot on. Turn this on. And so how you do that is you put your cursor on it and you press enter, and that highlights it like this. So when it's highlighted, it's turned on. When it's not highlighted, it's turned off. Okay, to get to this window over here, you actually go to the window button. That's right next to y equals. Now, most of the time when we're doing regressions, we're talking about real-world data, and real-world data doesn't typically fit between -10 and 10. So what we have to do to be able to see the data that we are graphing is to change these values here. So this is your domain, and this is your range. So what you're going to have to do is put in the smallest x value you have in the table, the largest x value you have in the table, smallest y, and largest y values. So you have to adjust these to be able to see those points that you are trying to graph. So again, all of that is to help you be able to graph the data that you are seeing in the table. To get to the actual regression and to type the data into the regression, we go to this screen right here. And the way we get to that screen is stat. And we're using that very first menu that we have right here, edit. and we do option number 1. Stat edit option number 1. That will take you to this screen over here. And when you get to this screen, we're going to enter our data. All right. List 1 is the X values. List 2 is the Y values. Once you get list 1 and list 2 in, we need to get to this screen. This is also going to stat, but this time we arrow over to the calculate menu. That's this menu right here. And then we look at our regression options. There's a few listed here, and then there's even more listed down below. And you're going to have to choose which regression it is that you are needing to do, either based on the shape of the graph or based on the common difference or common ratio, which we're going to work on a little bit in a minute. So we're actually going to write some information about that down here. So how to choose the regression type. If you have a graph, you're going to do what we started the lesson with today. You are going to look at the shape of the graph. Okay, and sometimes the shapes are very similar, what we saw in our examples for today. So you have to look and see which one's going to be the better fit. All right, that's if you have a graph. If you don't have a graph, you're going to have a table of values. And when you have a table of values, sometimes you can do what is called the common difference or ratio. And we're actually going to work on that in page 2. So once you choose your regression type and we select that from the menu up here, you're going to get to this screen here. This screen is going to look very much the same for any regression. Up here it tells you what kind of regression you did. So you leave X1, Y1, and frequency list, you leave those alone. If you want to store the regression equation to graph it, we're going to put a Y1 in there. And the way that we get to that Y1 is we go to alpha and trace. And then you just press enter. Alpha trace will get you the Y1 that you need there. Not necessary, but it is kind of handy. Okay. Down here on the calculate menu is where you're going to need to press enter. That's actually telling it, hey, it's time to go. Let's get this equation finished or done here. Once you press enter, you're going to get a screen that looks like this. Again, most of the screens are going to look fairly similar. It'll tell you what kind of regression you did up here. It will give you the outline of the formula here. And then it will tell you what each one of the variables equals. Now you guys may or may not see these guys. Those are not by default turned on in the calculator, but just to kind of talk about these, there are statistics that you're using as far as the data is concerned. I like the R the best because it tells you the, it's called the correlation coefficient. It tells you how close the data is fitting the model, or the model is fitting the data. So if I took this number and turned it into a percentage, I'd move the decimal back 2 places. That's actually 93%. So what that's telling me is based on the data that I entered up here in my lists, the model fits the data about 93% accurately. That's a pretty good fit as far as real world data is concerned. Okay, so that's, you might see an R in there. We're not really going to go too much into it, but I thought it'd be good just to introduce that for those of you who may do statistics. Correlation coefficient is a big deal. All right, we are focused on the y equals and then any variables that they give you. So you're going to take those variables and you're going to plug them in place, or the numbers here, and you're going to plug them in place of the variables up here. That gets you your regression equation. So what happens if I don't give you a graph? You do what now, Sterling? What were you saying? So you can plug in the information from the table, right? So if I just give you a table of values, Now what happens when your exponential and your quadratic look a lot the same? How do you know which one to choose? Right? Okay, so I'm actually going to show you guys a way to be able to algebraically figure out if it's linear, quadratic, or exponential. Those are our only three options from this point on. I think so. Way back. Okay, so it says when given a graph, we can easily make an educated guess at the type of function based on the shape. When we just have a table of values, we have to do a little investigating. We're going to look for common differences or common ratios. If it is a first difference that is the same, so your first difference stays constant, that is a linear set of data. If your second difference stays common, or constant, sorry, that is quadratic data. If the first and second difference don't stay common or constant, but you have a common ratio, that is exponential data. So let's talk about how we would figure each one of those out. So if you'll come down here on number 1 and 2, it says determine the type of function. And again, our only options are linear, quadratic, or exponential. Okay? So the first thing you look at is, do the x values go up by the same amount each time? Yeah, 6 to 7 to 8 to 9, are they going up same amount? Okay, then we take a look at our y values. How much is my y value going up from 34 to 47? What's that difference? 13. What about from 47 to 62? What's that difference? 15. From 62 to 79, what's that difference?
17.
17. From 79 to 98. 19. And from 98 to 119. 21. All right, this is called the first difference. If the first difference is constant, then my data is linear based off of what we wrote up here, the first difference. We're looking for the first difference to be constant. In other words, the same number. Did I get the same number for each of my differences? No, for here I got 13, here I got 15, here I got 17. Did I get the same number each time? No, so my first difference is not constant. Okay, so let's try a second difference. So the second difference is the difference of the differences. So these were my differences right here. Now we're going to do the difference between those. So from 13 to 15, what's my difference? 2. From 15 to 17? From 17 to 19. And from 19 to 21. This is my second difference. Is my second difference constant? So my second difference is constant. Therefore, that's what the 3 little dots in the triangle mean. What kind of data do we have if the second difference is constant? Quadratic. What we said up there at the top. Okay, therefore, quadratic data is what we have. So determining the type, it is quadratic. Why is it quadratic? So that's the explain your reasoning. Why is it quadratic? Because the second difference is constant. Okay? Do you guys follow me on that? Does that make sense? Okay. Then try to find for me the first and second differences on number 2. Or first difference, and if it's good, then you can stop. How do we talk a fraction in the calculator? Because I'm totally fine with you doing that, but they are all common denominator, so that makes it a little nicer. Alpha y equals will get you a fraction. But you can notice 1/5 to 3/5. What's the difference in the numerators? 2/5. So really all you need is your numerator because it's a common denominator. Okay. So go through and do the first differences for me. If they're constant, then what kind of data do you have? Linear. If they're not constant, then you're going to do a second difference. All right, my first difference is constant. Now, I got 2 fifths, 6 fifths, 18 fifths, 54 fifths. What's this one?
162 fifths.
162 fifths. So my first difference, not constant. Okay. What about my second difference? Oh, Trace, you're shaking your head. That one didn't stay constant either.
No.
So here we have a 4 fifths. Here we have a 12 fifths. I always do a few just to make sure that I'm not being goofy and wrong in my arithmetic. What's 54 minus 18? 32?
36.
30, 36? 36. 36 fifths. Is this one staying constant? So my second difference is also not constant. So that means it must be what?
Exponential.
It's not linear, it's not quadratic, so it must be exponential. Now here's the way we can show that it's exponential. You're going to start with this last number right here, and you're going to divide by the number that's in front of it. So I want you to divide here. So 243 fifths divided by 81 fifths. Alpha y equals will get you a fraction box. So in your calculator, do 243 fifths divided by 81 fifths. What is that value?
3.
Should be 3. So I'm going to put a little 3 in here. I'm going to change that color. Let's go pink. Alpha y equals gets you a fraction. Okay. So the common ratio looks like it might be 3. Let's try it again. 81 fifths divided by 27 fifths. And if you'll notice, it's really just the numerator, right? What's happening to the denominator? Yeah, so it divides itself out. So 81 divided by 27 is 3. 27 divided by 9, also 3. 9 divided by 3. 3 divided by 1. 3. That is our common ratio. And it stays, I'm going to say it's staying constant. Therefore, because my common ratio is staying constant, what is this? What kind of data is this? This is exponential. Okay. So I think you guys are okay with the what, whether it's linear, quadratic, or exponential, but you got to be okay with the y. Okay. And the y is the common ratio or common difference or the second difference. I added this problem after I did a copy of the notes. We're going to do this one and a couple more and then call it good for the lesson. This is not what you guys have on your note copy. So if you would either scratch out what's on your note copy, put it off to the side. We are not doing recursive data. So at the bottom of page 2 where it says to use the table and do recursive data or something along those lines, we're not doing that. So if you could write this table in on your notes, and I just want to take a few minutes to make sure that you guys are okay making a logarithmic function in the calculator. So we're going to, everybody go through and do this one together in your groups and make sure that you guys are able to get this logarithmic function. So again, we're adding this problem at the bottom of page 2 instead of the recursive problems that you guys had before. All right, if we have gone through the process of doing the logarithmic equation, what you should have gotten is y equals 76.213 plus, nope, minus, because this one's negative, minus 29.863, and then we have ln of x back behind it. So pretty much page 3 is going to be a repeat of everything we just did. Steps on 1 and 2 up here, it says determine the type of function. That's where you're going to do a first difference, second difference, or common ratio. So that's what you would do on these two. Do y'all feel like we need a little more practice on that? Or are we feeling okay about first and second difference and common ratio? Feel like we're good? So when you see determine the type of function, that's where you do first difference, second difference, or common ratio. Okay. Same thing on the two below that, only it's narrowing it down for you. On the two below that, it says determine whether the data is exponential, which means all you have to do on that one is the common ratio. And if the common ratio is constant, then it is exponential. If it's not constant, it's not exponential. Those are the only choices you have for those two problems. Then it says write a function that models the data. That's where you're going to go to the regression. Okay, so that's what you would do in a problem like that. So that's kind of combining what we did on page 1 with what we did on page 2. All right. Number 12, it says use a graphing calculator to find an exponential model. So it's telling you exponential, model is the regression, and it's just telling you what type of model to use as exponential. Right? Are we feeling comfortable with the calculator steps to the extent that since we haven't necessarily done an exponential model, are you guys still okay being able to put an exponential model in there? Okay. Again, they're giving you a table of values. They're just giving it to you in a real-world situation. So a doctor measures an astronaut's pulse rate, which is the Y, in beats per minute at various times X in minutes after the astronaut has finished exercising. The results are shown in the table. Part A, use a graphing calculator to find an exponential model. So again, model tells me to do a regression, and it's telling me what kind of model to do. So I'm doing exponential. All right, so go ahead and get this data typed into stat for me. And let's see if we can come up with a model for this data. Give me an exponential equation. All right, so in the calculator, the exponential model looks like this. Y, and then you have A, and then B to the X, or it uses a multiplication symbol in here. I like the parentheses better. I just think it's cleaner, but you can use the multiplication if you want to. So y equals our A value we should have gotten is 153.075 if you are rounding to 3 decimal places. Then you're going to do a parenthesis. Your B value is 0.934. And then we're raising that to the X power. So there's your exponential model. All right. This is exponential, so quick review, is that exponential growth or decay? Ah, that one is decay. Why?
Going down.
It is going down. If you look at this value right here, this is less than 1, so that's what's telling me it is decay. Okay, you can also think of it in reasonableness of the situation. If the astronaut was exercising and is no longer exercising, what should be happening to his heart rate? It should be decreasing, right? Okay, so part B, use the model, so the equation we just wrote right here, to predict the astronaut's pulse at 16 minutes. 16 minutes, are they giving me the X value or the Y value? They gave me the X, so we're plugging it in place of the X here, and we're getting the Y, the pulse rate here. So we're going to plug into the calculator in place of the X, we're going to put 16. So type this into the calculator. using a 16 for the x. So this is where the models would come in handy, is if we're trying to predict outside of the data that they gave me. So 51.3, so it looks like. All right. Last question on here. Is it reasonable to use the model to predict the astronaut's pulse rate after 1 hour? Why or why not? What you got, Ben?
No, because number one, his pulse would be at 2.577 beats per minute, which is
Okay.
humanly possible with a resting heart rate.
Okay. So how'd you find that his heart rate would be 2.5 beats per minute?
I just went all the way down to 60 on the table.
So you went to the table and then just scroll down to 60? Okay. If you type in, so 60 would obviously be 60 minutes, 1 hour. If you put a 60 right here, you're going to get out an x value, or sorry, a y value of 2.5. That's 2.5 beats per minute. Is that reasonable?
If you're dead.
No?
That means beat, and I'm going to wait 30 seconds.
No, it's not.
Beat, right? Does that make sense?
Yeah.
That's what you're looking at as far as the data is concerned. So if you're almost dead, maybe, right?
No.
Okay, so would it make sense for me to use that model long term?
No.
That's what the question's asking. Does it make sense to use that model long term? No. So when you do models that represent data like this, they're good for outside the data, but only so far outside the data, right? It's not going to make sense for you to go way outside the data because it's not going to give you an accurate representation. So I think what I would say there, kind of like what Ben had said, is it reasonable? Not reasonable because beats per minute would be 2.5 based on the model. It's too far outside the data given. Give that one a shot for me real quick, guys. So we're doing the same thing. I just want to make sure that you guys know how to do those. I know y'all know how to do the regression, but how to use the model is what I'm looking for on this one. Make sure you guys are good with that.